Okay, so before I start, I think I need to probably, well, I do need to make a correction from last time, and the correction is that so we were talking about Gauss's law, and the Gauss's law is essentially, we are saying the divergence of E is 1, I think it's something like 4 pi q by epsilon delta 3 of x. Okay, so I think I didn't emphasize the fact that it's a 3-dimensional delta function. So that when you integrate over all space, the right-hand side just becomes 4 pi q over epsilon. Okay. Okay, any questions? Or epsilon what? Okay. I think, yeah. Okay, so any other questions?
Sir, is it possible to upload the lectures in 1-hour version before adding the quiz so that we can watch earlier the rest of the videos?
In fact, the lectures, if you subscribe to my channel, sorry, this is I think this is q over 4 pi epsilon. Yeah. So if you subscribe to my channel, so my YouTube channel, which is associated with my BRAC email account, and it's I'll post a link. Then I actually I've uploaded a lot of the videos already. Okay. So what I'll do is that I'll post that, and there's a playlist called Quantum Mechanics 1. What I'll do is that I'll post the link for that. Okay. So, and you can just, if you want, you can follow that. All right.
Okay. I was thinking that to ask questions from previous class, I had to rewatch the previous class, but I couldn't. So the questions will, কোশ্চেনগুলো জিজ্ঞেস করতে দেরি হবে, আর 2-3 ক্লাস পর একটা লেকচারের কোশ্চেন আসতে পারে।
Okay, yeah, I'm very sorry. I'll catch up, but now if I figure out a way to post the raw lectures earlier, maybe it's yeah. So Otonu has posted the link to the playlist in the chat box, but I'll post it on Slack. Okay, so let's just talk about, last time we discussed some issues about delta function, and I just wanted to start today with an application to quantum mechanics. Okay. So in the tutorial, you saw that you found that there was a good justification to interpret this formula as the delta function, right? And similarly, we can say 2 pi, 1 over 2 pi, the integration of E, doesn't matter what the sign here is. So this is symmetric between the position space and the momentum space, okay, or wave number space. Now, so let's apply this to quantum mechanics. So in quantum mechanics, we want to change our variable from k to p. And if you do this, then our, say, this relationship becomes 1 over 2 pi h bar. Now the integral goes from minus infinity to plus infinity, e to the power I by h bar, p minus p prime of x, and then d of x, and here we have d of p minus p prime. Okay? And so now what we can do is that we can say, okay, let's take a wave function at the time t0. So wave function describing a particle, okay? So psi is x at time t0, and it's going to be given by, if I change the variable from k to p, now the Fourier coefficients are functions of, so this, say there's a cubed here. Let me just specialize to one dimension, and and then we can do the 3 dimensions, can be generalized easily. So this is just one dimensional. So here we have square root of 2 pi h bar. And then we have an integral over momentum space with the Fourier coefficients ap, and then e to the power I by h bar px of dp. Okay, so this is my wave function at t equals to 0. Now we know that this wave function as a function of t has this form, right? This solves the Schrodinger equation. In fact, that's how we derived, quote unquote, derived the Schrodinger equation. Okay, so each of these factors will evolve in time to become this. So the wave function by linearity, because Schrodinger equation is a linear equation, if each factor evolved to become this, the evolution of the whole thing would be the same linear combination. So this will be given by 1 over square root of 2 pi h bar integral over a of p, but now e to the power I by e to the power I by h bar px minus e of t d of p. Okay, so this is the solution to the Schrodinger equation for any arbitrary time, given that at time 0, this is the solution. Okay? So now we want to find, A of p. So the way we do it is that we take this expression and multiply both sides by e to the power minus I by h bar p prime of x. So if I multiply both sides and then also by square root of 2 pi h bar, then on the right hand side I have 1 over 2 pi h bar, and then we have a of p, and now I have e to the power I h bar, and in the bracket now we have p minus p prime of x, and then we have minus I et by h bar. And then we have dp. But once we have done this multiplication, what we want to then do is that we want to integrate both sides with respect to x from minus infinity to plus infinity. So it's a double integral. Okay? So what happens as a result? Well, we see that this is a function of p. So in this integral, we can say, well, let's separate out the p integral first. And this depends on p. And e implicitly depends on p because it is some function of momentum. So let me just, it doesn't depend on x, so I can, I can also factor this out. And then inside the x integral, we have e to the power I by h bar, p minus p prime of x. And so this guy times this guy is just a delta function of p. So we have d of p, a of p, e to the power minus I by h bar e of t, delta of p minus p prime. And now if I do that p integral, I get a of p prime, and here I've got e to the power minus I by h bar, e, which is a function of p prime and t. And on the left-hand side, I have 1 over square root of 2 pi h bar integral over x of psi of x of t e to the power minus I by h bar p prime x. So now I can cross multiply this guy, and then I have an expression for AP, which is given by 1 over square root of 2 pi h bar minus infinity to plus infinity d of x psi of x of t e to the power minus I by h bar p prime x minus e of t. Sorry, let me just. So sorry, we have changed the variable here from p prime to p. So this is going to be e to the power minus I by h bar px minus et. Okay, so and this is the expression for AP. So AP does not depend on time, and that's because the time dependence of this factor and this factor, they cancel out.